Today we will discuss some more results about covering projections. So we have following theorem. If X is locally connected a continuous map P from X tilde to X is a covering projection if and only if for each component C of X, the map P restricted over P inverse C from P inverse C to C is a covering projection. So if X is locally connected, so what is a locally connected space? To recall, a space X is called locally connected if every so a space X is called locally connected at some point X in X if every neighborhood, right, of X has a connected neighborhood contained in that. So for every neighborhood V of X, there is a connected neighborhood U of X with U contained in V. That is, every neighborhood of X contains a connected neighborhood of X. And if X is locally connected at each point, then it is called locally connected. Proof. Let P be a covering projection. And C be a component of X. Since so if you have a locally connected space, then its components will be open. Since X is locally connected, uh, each of its components are open. There is a connected open neighborhood. Uh, since X is locally connected, each of its components are open, and in particular C is open. C is open, right? Now, we want to prove that this each point of C has a has an evenly covered open neighborhood in C. So for every X belonging to C, there is an evenly covered open neighborhood V of X in S. Then, so if V is an evenly covered open neighborhood, right? Then every uh, open subset of V is also going to be evenly covered. Then U equal to V intersection C is open and evenly covered. Hence, P restricted over P inverse C uh, from P inverse C to C, then this this is open in C as well as X, right? And evenly covered by P. Right. Now this P inverse U, right, will be an open subset of, means the P inverse U can be written as, because by P. So because V is evenly covered by P, so U will be evenly covered by P, and because P inverse U is the disjoint union of open sets, each of which is homeomorphically mapped onto U by P. So it means that P inverse U also will be an open subset of P inverse C, because U is subset of C, so P inverse U will be, so clearly P inverse U is open. U is open subset of P inverse C and evenly, and U is evenly covered by P restricted over P inverse C. So one side we have proved. Now we will assume that every component, for every component C of X, this is a covering projection, and then we'll prove that P is a covering projection. Conversely, assume that P restricted over P inverse C from P inverse C to C is a covering projection for every component C, for every component C of X. Now let X be a point in X, then X belongs to C for some component, because X is the disjoint union of its components. So X is going to be in some component of X, capital X, C of X. Since this is a covering projection and X is a point in C, and there exists an open set U in C such that C containing X and evenly covered by P restricted over P inverse C. Since C is a component of a locally connected space, C is open. Since C is open in X, U also is open in X. So if C is a subspace of X, because C is open, so every open subset of C will also be open in X because open subsets of C are of the one B equal to uh, C intersection A, right? Where A is so if B is an open subset of C, then B will be of this form where A is an open subset of X. Now, if C is open, then A is an open subset of this, then the intersection of two open sets is open. So B will be open in X also. So U also is open in X. And clearly this clearly U is evenly covered by P, right? Because it is completely contained in C and it is evenly covered by P restriction of P over this. So definitely it will be evenly covered by uh, your P. So this completes the proof. Right? So hence P is a covering projection. Because if you consider this your P inverse, if you consider P inverse U, this is nothing but P restricted over P inverse C, inverse of this applied over this, right? Now because your this is because P inverse C, right? P inverse U is an open subset of your P inverse C, right? And you can write this P inverse U disjoint union of open sets in P inverse C, but P inverse C is open in X tilde, and every open set in P inverse C will be also be open set in P X tilde. So P inverse U you can write as disjoint union of open sets in uh, X tilde, each of which is homeomorphically mapped onto U, because each of them are homeomorphically mapped onto U by this restriction. Now we have following lemma. Let U be an open connected subset of X, which is evenly covered by a continuous map P from X tilde to X, then P maps each component of P inverse U homeomorphically onto U. So, proof. Since U is evenly covered by P, uh, this P inverse U equal to union of uh, this alpha V alpha where V alpha intersection V beta phi if alpha is not equal to beta, and if 1 alpha 2, let me write like this. If alpha 1 not equal to alpha 2 and P restricted over P alpha from V alpha, P alpha is a homeomorphism for every alpha. Also, V alphas are open, right? V alpha open in X tilde for every alpha. Right. Now, because this each V alpha is homeomorphic to U and U is connected, right? So since each V alpha is homeomorphic to U and U is connected, each V alpha also is connected, right? If two spaces are homeomorphic, then if one is connected, then another also should be connected. So each V alpha is connected. So what you have? You have P inverse U equal to union of these V alphas. Each V alpha is connected and it is open in X. Hence, they are disjoint from each other, right? It means these V alphas, they are the components of this P inverse U. Since V alphas are open and disjoint, each of the V alphas is a component of P inverse U, right? So it means that these V alphas are components of P inverse U, and these components are homeomorphically mapped onto U. So this completes the proof. Next, we have following corollary. Consider a commutative triangle tilde to tilde P P1 P2. So suppose that we have a commutative triangle like this, where X is locally connected and P1 P2 are covering projections. So P1 from here to here is a covering projection, P2 from here to here is another covering projection. Now, if P is a surjection, it is a covering projection. It is a covering projection. So let us prove. So to prove that P is a covering projection, we have to prove that every point of x2 tilde has an open neighborhood which is evenly covered by P. So let Y be in x2 tilde. Then P2Y equal to X in capital X is evenly now, because P2 is a covering projection and P1 is a covering projection and X is a point in X, let U in X be a connected open subset of X containing X and evenly covered by P1 and P2 both. So this we can do because P1 is a covering projection. So there will be an open set. There will be an open set U1, right, containing X, right, which will be evenly covered by P1. Similarly, there will be an open set U2 uh, containing X and evenly covered by uh, X and evenly covered by this P2. Now, this uh, we can choose this uh, U1 intersection U2, right? So this is going to be this is going to contain X, and this will be evenly covered by. You can verify. It is straightforward. This will be because this is open subset of this. This is open subset of this. So and they are evenly covered by P1 and P2 respectively. So this will be evenly covered by P1 as well as P2. Now uh, we can find the component of U1 intersection U2 which contains X, right? So that component is going to be open, right? Of course, connected, right? So, and that is going to be evenly covered by P1 as well as P2. So we can get always a open connected uh, subset of X which is containing X which is evenly covered by P1 and P2. Now, now we have following thing. Uh, Now we have this U here, which is evenly covered by uh, P1 as well as P2, and P2 inverse U equal to union of uh, V alpha and P1 inverse U equal to uh, union of W beta, right? Uh, where V alphas are disjoint uh, and W betas are disjoint disjoint and P2 restricted over V alpha from V alpha, that is joint open to U is homeomorphism. Also W betas are disjoint open and P1 restricted over W betas from W betas to U is a homeomorphism. Now, what you have here, this is this implies, so P1 is what? Because this diagram is commutative, so you have P composed P2 inverse U equal to union of this W beta, which implies P inverse P2 inverse U, this you can write like this, equal to union beta W beta, which implies P inverse of this P2 inverse U is this, the union of alpha V alpha equal to beta W beta, which implies this you can write as union of alpha P inverse V alpha equal to union of beta W beta, right? Now, now this, so choose, let uh, y belongs to, so because y is going to be in some v alpha, right? So let y belongs to v alpha naught, right? Then this, now P inverse v alpha naught, this is connected, right? This is connected, uh, sorry, this V alpha naught, right? So this V alpha naught, they are because U is open connected. So P2 inverse U is disjoint, is union of. So I need maybe 5 minutes more. Okay, so because we have very less time left, so in 30 seconds, so I leave it for you as an exercise, right? So now this is equal to union of W beta I, where each P restricted over W beta I from W beta I to, right? Now, if P inverse V alpha naught intersects some W beta, then it must contain because this W beta, right? You see here that because we have this, so if you apply P, right, over some W beta, right, then what you will have, so we have here, if you apply P over this union beta W beta is your union beta P of W beta, right? So these W betas, they are connected, okay? So P of W beta also will be connected, right? Now, if if W beta is if there is some W beta which intersects P inverse V alpha naught, right? So if some W beta intersects P inverse V alpha naught, right? Some W beta intersects, and if W beta is not completely contained in this P inverse V alpha naught, then P of W beta means what? Means P of W beta uh, will be will intersect V alpha naught as well as some other V alpha, right? But that is not possible because V alpha naught and those that other V alpha, right? They are disjoint, and this W beta being connected, P W beta will be connected. So if this intersects some W beta, then it must contain it, right? Hence, hence P inverse V alpha naught equal to union of W beta I, right? For some beta I, because this is completely subset of this, right? Every point of it will be some point of W beta, some point of some W beta, right? So we have to have this because of this line. Now, P restricted over, because obviously this W beta is, they are open in uh, uh, your x1 tilde, and P1 restricted over W beta I, from W beta I to V alpha naught, right? So this is bijective. Why? Uh, because if this is not bijective, then if you compose this with this uh, P2, right? Because this this P composed to restricted over W beta I from W beta I to U, and P2 restricted over V alpha naught from V alpha naught to U R by G, right? So you just see here that because P1 restricted over this, it is bijective, in particular injective, so hence P becomes injective, right? And if your so P is injective, and hence this restriction is injective. Now, because this P1 is surjective, this P2 will have to be surjective. P2 is of course restricted over this is bijective. So yeah, so you verify this. This is because of these two. Now this becomes bijective. So what we can do is, this. Now from here we have now P1 restricted over W beta I equal to P2 restricted over V alpha naught composed P restricted over W beta I. So from here we have this, and this is a so P1 restricted over W beta I equal to, because this is a homeomorphism, so you can consider inverse of this. So this is P2 restricted over B alpha naught inverse compose P1 restricted over W beta I. Right. So this is homeomorphism. This is homeomorphism. Hence composition is a homeomorphism. So because this P2 is yes. So this observation is enough. So this was not required, right? This is not required. This is not required. We have this. So this, hence P1 restricted over P restricted over W beta I from W beta I to V alpha naught is a homeomorphism. So this is true for every beta I here. Hence V alpha naught is an evenly covered open neighborhood of Y by P. Hence P is a covering projection.